Hi, welcome to my channel, JaberTime. I'm gonna go over Green's theorem. The main thing is right here, this formula, and here's an example what the Green theorem talks about. Let's get into it. Green's theorem gives the relationship between a line integral around a simple closed curve C and a double integral over the plane region D, bounded by C. C is given by the vector function r of t, where t goes from A to B, with a positive orientation. Positive orientation means you're going counterclockwise, tracing C, and as you do that, the region D is always on your left. Let C be a positively oriented, piecewise smooth, simply closed curve in the plane, and let D be the region bounded by the curve C. This is positively oriented. You could see we're going this way, counterclockwise. This is a negative orientation. The arrow is going up this way, so we are going clockwise. That's a negative orientation. That's a positive orientation. And Green's theorem deals with positive orientation. If P and Q have continuous partial derivatives on an open region that contains D, then this is what Green's theorem says. The line integral of P dx plus Q dy is the same as the double integral over D, the region D, of dq dx minus dp dy. dA. What this says is the following. Instead of integrating as a line integral around the curve C, the closed curve C, you could just walk inside and do the double integral with respect to A. So it's kind of like the opposite of the fundamental value theorem. The fundamental value theorem part 2 says the integration from A to B could be done as by finding the function and plugging in the endpoints, which is B and A, f of B minus f of A. This one takes you from the boundary, which is kind of like the endpoints A and B, the boundary line, inside. So instead of going from full integration to a simple one, let's say at the endpoints, this is kind of like the endpoints C, he is doing it the other way around, which is interesting. Now, this is what we have. Notice that the left side of this equation, which is in green right here, is another way to write the line integral f dot dr. So keep this in mind. F dot dr is the left hand side. Sometimes they will say find f dot dr using Green's theorem. Well, this is what you have, especially if your function is pi plus qj. We also sometimes, using Green's theorem to say positively oriented, we draw a circle over the integral symbol. Sometimes we add even the arrow on it. Here's an example. Evaluate the line integral of x to the fourth dx plus xy dy. That to me is p of xy. That to me is q of xy, where c is the triangular curve consisting of the line segments from 0, 0 to 1, 0, from 1, 0 to 0, 1, and from 0, 1 to 0, 0. To see what they're talking about, here's a graph. C is the triangular curve, so we're gonna go from this point to this point, then from this point to this point, then back from this point to this point. That is called positively oriented, and it's a closed region. I'm adding more details to it so I could go faster in calculations. This would be my y1, which is 0. This would be y2, which is 1 minus x. Where did I get this from? Since you are crossing at 1 here and crossing at 1 here, the graph is going down with a slope of -1. and the y-intercept is 1, and that's why the equation for this line is y equals 1 minus x. Now p of xy, as I mentioned earlier, is x to the 4, and qxy is xy, x times y. dp dy is 0, there is no y involved. dq dx is just y. The derivative of this with respect to x will be just the y. Now we'll just apply the formula or the theorem. This is the line integral in general, and this is how we're going to apply it. dq dx is y, we found it. dp dy, which is 0, as simple as that, y minus 0. Now I'm using the type 1 integration, double integration. So I'm going to go dy first from y1 to y2, from y1 to y2. Once I finish, I'm going to apply dx from 0 to 1. Y to the second over 2. Plug in the limits. I get 1 minus x being plugged in here, and I pulled the half all the way outside. No worry about plugging in 0. Integrate this. You could have two options. Either you expand this and do it as a polynomial term by term, or use u substitution. 1 minus x will be u, and there is a minus sign that has to show up outside, and this is what I mean. This is a minus sign. So I use the u substitution. That's going to be u to the third over 3, and that's what I have. Plug in 0 and 1, take it back to 0 and 1. The answer is 1 over 6. Now, Green's theorem is not the line integral. It switches from line integral to double integral inside. Back 2-3 sections ago, we have line integral. It doesn't hurt to visit, so I'm gonna go back and revisit the line integral, and I'll take maybe, I don't know, maybe 2 minutes to show you. That's why I'm not spending too much time on the coming one using line integral. It's the same problem. It doesn't hurt to connect ideas together. And since this is not our topic, I'll go a little bit fast. You could stop the video or look at the notes by hitting the spacebar. Here we go. So we're doing line integral this time. First, second, third. I'm using different colors to tell you which one is which. Along C1, we're gonna consider x equals x. That's my variable. X changes. I'm gonna keep y equals 0 because I have to. Y equals 0 as I'm walking this way. That says that dx equals dx. That's my main variable. And there is no y. dy is 0. X will vary from 0 to 1. The integration along C1 will be x to the 4th dx, and this is gone. Y is 0, right? Just do the math. X to the 5th over 5 from 0 to 1 will be 1/5. Now, along C2, I have the following. I said let's x equals x, and let y equals y minus, let y equals 1 minus x, where x changes from 1 to 0. If you look at the x's, from 1 to 0, going this way, that's how I have it. So dx is dx, dy is minus dx. That's something that you have to be careful and pay attention to. Just go in and change dy to minus dx, change y to 1 minus x, and now everything becomes one variable, which is dx. Integrate with respect to x. I have it. Plug in 1 and 0. Do the common denominator between 5, 3, and 2, which is 30. Multiply by 6. Multiply by 10. And multiply by 15. I ended up with negative 1 over 30. Let's go around C3. Along C3, y is y. My variable is y. X is 0. But if you look at it, x is 0. I don't have to worry too much about more detail. The equation is of this format. Look at it here. X is 0, everything cancels. So integration of 0 dy, because my y is my variable, it's just 0. Now I have 1/5, and I have negative 130, and I have 0, and I need to add them up. Adding them up, I use a common denominator, times 6 times 6, 6 over 30. That's minus 1 over 30. And that's, of course, 0. 6 minus 1 is 5. So 5 over 30 divided by 5 divided by 5, 1 over 6. Same answer. Hopefully, it was helpful, and probably you know why I'm going too fast, because that's Green's theorem video. It's not line integral. So, evaluate the line integral positively oriented of this package. It's kind of hard to read it quick, but that's my p of x, y, and that's my q of x, y. Where c is the circle x squared plus y squared equals 9. You know, the circle centered at the origin with a radius of 3. This is p of x, y. The derivative of p of x, y with respect to y, there is only this term has y in it, so it's a 3. This at least shows you how the double integral using Green's theorem simplifies this whole package to a simple double integral. Here we go. The integration of q with respect to x, this term has an x, this term does not have an x, so it's just 7. Now, dq dx minus dp dy, 7 minus 3, just a 4. This is simple math, that's why I'm trying to save you some time. Take the 4 out, split them, because this does not communicate with r, this does not communicate with theta. Do the math, and it's 36 pi. Here's something interesting that it's good to know. Sometimes you want to save yourself some time if you know what is happening and you want to just do it without calculations. You see how long it took me to integrate this right here, which is actually this 4dA. I'll show you a quicker way. Here we go. Instead of using polar coordinates, we could simply use the fact that D is a disk of radius 3 and write the double integral of 4dA as 4 times. Take the 4 outside. That's a double integral of dA, which is the area of the disk, which is pi r squared, but r is 3. 3 squared is 9. 9 times 4 is 36. Same answer, 36 pi. So, it's good to know. I mean, it's just a comment. It's an idea that sometimes you want to save yourself some time and do it. We're going to apply it in another example coming. Here's an example. This is p of xy, this is q of xy, where c is the boundary of the semi-annual region D in the upper half plane between the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. Upper half, I think the graph says it, so instead of reading it again, we are here. This is my region D. Imagine if you want to do a line integral, they're going to go over maybe C1, then C2, then C3, then C4. So you're going to have 4 integrations, and each one you have to do the math to apply it correctly. Instead of that, we're going to apply Green's theorem. Knowing that D, the region D, could be described as r theta, where r ranges from 1 to 2, and theta ranges from 0 to pi. Now we need to focus on P and Q and do the math on the side. dP dy is 2y, dq dx will be 3y. Now let's go back to the problem and do the work. Here's the problem, line integral. We're gonna change it to double integral with d dx of q minus d dy of p, which we're done on the left. So I have 3y minus 2y, just 1y. Okay. Now, of course, if we could find the area here quick, we could do that and apply it and finish. We can. But let's move on and do it with polar coordinates. Y is r sine theta, and dA becomes r dr d theta. r goes from 1 to 2, and theta goes from 0 to pi. Now we could separate them just like this. This does not communicate with theta. This does not communicate with r, so I could separate them. Do the math. Minus cosine r cubed over 3. And you end up with 14 over 3. One more. Here it says use Green's theorem to evaluate f dot dr. If they say that, that is actually the line integral of p dx plus q dy. This is my p of xy, and this is my q of xy, where the circle is x minus 5 to the second plus y minus 2 to the second equals 25. So it's a circle with the radius of 5, shifted 5 units to the right and 2 units up, oriented counterclockwise as what Green's theorem is stating. So this is the function with I and j instead of those symbols, and we're looking at the same circle that I mentioned, and C is oriented positively. So f dot dr, we use p dx plus q dy, and now we apply Green's theorem. We need the derivative of q with respect to x, as you could see, minus the derivative of p with respect to y. To do that, I got the following, and the reason why I got them is from the following. The derivative of tan inverse, because arctan means tan inverse, of x, just to remind you, is 1 over 1 plus x to the second. The derivative of ln x is 1 over x. Well, of course, we don't have x here, it's y over x, and here it's x squared plus y squared. You're going to consider this as a u substitution. You're going to consider this y over x as a u substitution. For example, if this is d dx of ln u, that will give me 1 over u times du dx, or u prime. So, just to see that it almost looks like it, 1 plus u squared, the derivative of y over x, because that's the u substitution, will give me minus y over x to the second. 2 goes to the front. 1 for y, derivative with respect to y. Derivative of this will be 1 over times the derivative of this in terms of y, with respect to y. That will give me 2y on top. That's the u substitution, gives you u prime on top. Okay, now if you apply the minus sign, distribute, that's going to be minus 1, and that's going to be plus. But when you do it as a plus, it's the same concept as this one when you rearrange it and make it clean. They cancel. So as you could see, sometimes the Green's theorem saves a lot of time. It changes everything from tan inverse and ln and so on to something that you could handle algebraically with fractions and so on and simplify. Okay, I'm not going to take the time to do this here. Trying to save you some time, guys. It's just algebra. You just do the common denominator and simplify it. It's the opposite of this with the minus sign in the front. Now what do you have? Minus double integral over the region D, which is a circle with radius of 5 dA. You could just apply the shortcut. That's a minus, and this is the area of D, which is the circle. Pi r squared, pi times 5 squared, minus 25 pi is the final answer. So it's about 20 minutes for Green's theorem. In the future, I'll be adding more examples as Green's theorem examples, I will call it. I'll see you on the next video. Thank you. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.